In this video, I want to talk about the idea of basic functions. So in the next video, we're going to be going through section 2.6, which is on transformations of graphs. And this section, as you can see, it starts off by wanting you to be able to recognize basic functions. And they list out some examples of basic functions here. F of x is equal to x, f of x is equal to x squared, x cubed, square root of x, cube root of x, absolute value of x, etc. And the idea is that so every basic function has a graph. They give the basic function here and a corresponding graph. And what we're going to learn in section 2.6 is that you can take a basic function and apply modifications to that basic function that do predictable things to the corresponding graph. For example, the graph shifts, just a rigid shift, left or right, up or down. So for example, the graph can be shifted along the x or y axis. The graph can be stretched or shrunk about the y or x axis. Or the graph could be flipped, like a mirror flip about the x or y axis. And once we're done with section 2.6, once you've watched this video, section 2.6, and worked some example problems, the goal is that you could take a look at any function, no matter what the function is, no matter how complex it is. You could look at its graph and its corresponding equation, and you could imagine that when looking at that equation, you could decompose it and see all of the translations, stretching, shrinking, flipping that's been done, and kind of see through that equation and see the basic function behind it. See the underlying basic function. That's the idea. But to do this, I first want to start out by making sure you have a solid understanding of what exactly a basic function is, because it's not so simple as just looking at this table here. So I wanted to make a separate video to go through this. Okay, now they're called basic functions here, but in reality, all of these transformations that we're going to learn, they apply to functions or relations. So for example, even the equation of a circle, we know that's not a function, but you'll have a basic form of the equation of a circle, and then from there you can apply modifications to that to shift the circle left or right or up or down, or even stretch the circle. And then when you stretch the circle, that makes an ellipse, right? Well, then from there you'll get the equation of an ellipse. And so just to give you a quick preview of these types of modifications that we're going to learn when we go through section 2.6. If you have, let's take f of x is equal to x cubed. So this is a basic form of a cube function. And I'll go into more specifics on exactly what I mean by basic function as we go through the video. But what makes it basic, you can think about, is, well, I could change the coefficient in front of the x cubed. Right now it's just 1. I could change that to 2 or 3 or 4. Or I could not scale it, like multiply by a number that's not 1. I could just say -1, or just put a minus in front. Or I could put a minus and scale it, -2. Or I could add or subtract a number just to the end of the function. Or I could f of x minus 3, I could add or subtract something from the x term. This is still the cubic function, the cubic basic function. It's just now that you got a -3 subtracted from the x. That's the kind of modifications that you do to a basic function that will translate the graph along the x or y axis, stretch or shrink the graph along the x or y axis, flip the graph about the x or y axis. Now again, this doesn't apply just to functions. You could do the same things with a relation. You could do this with any graph. So what we're thinking about is any equation, function or not function, any equation, you can apply these transformations that we're going to talk about. The types of things we just went over. You can do that with an equation, with a function, or just a regular equation that's a relation, like the equation of a circle. But this also applies for greater than 2 dimensions. So, okay, we know like a relation has to have at least 2 variables in it, because only with two or more variables can you be relating like an input to an output, like an x to a y, for example. But a relation is also anything with more than 2 variables. You're relating, like for an equation with 3 variables, you're relating two inputs to an output. Given an XY pair, so you can graph that. Given a point on the plane, you go up or down in the z direction. So with an equation in 3 variables, that has a graph in 3D, a 3D shape. And every principle that we're going to learn in the next video for translating a graph, stretching, shrinking, etc., applies in 3D as well. You could translate along the X, Y, or Z axis, stretch or shrink along the X, Y, or Z axis with the exact same methods. But if you have an equation in more than 3 variables, 4 variables, 5 variables, you have to think about it abstractly. So you're going to be translating it, quote unquote, about the 5th dimension. You can't really actually picture that, but it's the same concepts. I'm going to stretch about the W axis. That's like let's say you call that's X, Y, Z, L, and W. There's an equation in 5 variables, and you're going to apply a stretch about the W axis. Well, you can't really picture that, but you can it's still the same idea. But for the remainder of this video, what I want to do is let's stay in 2 dimensions. So just XY pairs, equations in 2 variables. I want to have some tunnel vision and just focus in on 2 dimensions just for the sake of analysis. And then after that, I'll branch out into more dimensions just to give you some big picture perspective. But for the time being, let's just stick with 2 dimensions. Let's have tunnel vision in 2 dimensions. XY pairs, equations in 2 variables, and 2D graphs. Okay, now, first of all, I don't like the term basic function because, again, it's not just functions, it's relations as well. It's any equation that all this applies to. And so what I want to do is I want to use some new terms. I'm going to use the term parent term and basic expression. Okay? And I'll explain what exactly these mean in a second. And you'll see why I want to use these names. By basic term, all I'm saying is that, like, here they give a basic function, f of x is equal to x. I'm just saying, let's take out this f of x and just leave x. So here's a parent term. It has no association with a function necessarily. And the graph here, you just set that parent term equal to y and graph it. So here's the graph of this parent term. If you want to make it a function, you can change y to f of x, but just for the idea of tabulating these basic terms, I want to leave out any f of x to imply that this could be part of a function or a relation. Okay, so we've got the basic terms, x squared, x cubed, square root of x, cube root of x, etc. Okay, but are these all of the parent terms? All of the possible parent terms? And furthermore, what do I even mean by parent term? Well, no, there's more than this. Okay, and I've made a table that shows all of the parent terms. We'll go through it in a second. But if you look at these terms here, what you notice is that each of these are like the most absolute bare bones basic form of one of the algebra operations that we sort of invented or defined in pre-algebra. So we started with x to the first, like just introduction to the idea of a variable. But then we said, okay, you could take a variable and multiply it by itself. So you could have x squared, x cubed, x to the 4th. The idea of raising a variable to a positive whole number exponent. But then we also talked about you could raise it to a negative whole number exponent, or even we talked about what x to the 0 meant. That's a constant, I guess here. Okay, the constant function. This would be like bx times x to the 0. So like this is x to the 0 with and you can put a 1, 2, 3, negative 1 in front of it. But yeah, so you had the idea of a negative whole number exponent. That's what kind of the idea of this reciprocal function is. 1 over x to the first, but you can have 1 over x squared, 1 over x cubed. But then we also defined the idea of the inverse of exponents, so radicals. And that's tied in with x to a fractional exponent, okay? We talked about the idea of the absolute value of a variable. And outside of pre-algebra in trigonometry, there's also the idea of sines, cosines, tangent, trigonometric functions, or you could call that a term. I don't have to say f of x is equal to sine of x. I could just put sine of x. So I could call this like a term, right? It is technically a function. It's the sign of, it is a function, but let's just, for the sake of argument, let's look at this as a term in the same way we're saying x cubed is a term. I guess you could say this is kind of like a function. You're taking a variable and cubing it, but for the sake of discussion, let's just look at both of these as terms. And what I mean by term is that, so if we come to the pre-algebra chapter, so here's an algebraic expression. This expression has 4 terms. An algebraic term is a product of factors that may include constants and variables. So technically the number 5 is a term, is an algebraic term, but really we're thinking about when we think about an algebraic term, we're thinking about something that has variables in it. But not, this is not a term, this is an expression. You're adding 2 terms. So it's just a product of factors, of constants and variables. Terms that have variables are called variable terms. A term that doesn't have a variable is called a constant term. And you have coefficients, is the constant factor within each term. Here the coefficient is -3, here -4, here 1, here this is like 5 times 1, you could say. So the coefficient is 5 on this constant term. But you see why I'm calling these parent terms. I'm calling this a parent term, this a parent term, because I want to separate it from the function, because these apply to both functions and relations. So I want to just look at it as just a variable itself. That's why I'm calling these parent terms. Using parent terms, you can create a function or a relation. You could take any parent term you want and make an equation out of it. That equation could be a function or a relation. But what do I mean by the term basic expression? Okay, well, again, an expression is you're summing or subtracting 2 or more terms. And what you can think about is that, so here's just some parent terms. I'm going to go over all of the parent terms in a second. But to have something that's basic, meaning that it's just the bare bones. The coefficients are all 1. You're not adding a constant. You're not subtracting anything from the variable. To have something that's basic, a basic function or a basic just equation relation, that's not a function, you don't have to have just a parent term. You could have some combination of parent terms. For example, I could add a cubic parent term to a square root parent term. Well, I can't simplify this anymore. But since, again, I'm not adding a constant to the end, I don't have, x plus 3 like this. I don't have a coefficient here. Since this is the bare bones, I'm not calling this a parent term, this is a basic expression. You see what I mean? And I could turn this into a function. Let's just say this is y, put a y here. This is a function because for every input you'd get 1 output y, even with this even root here because it's a principal root symbol, right? You don't get 2 values. But again, if I graphed this, that graph and this corresponding equation here, that's the basic, well, I could call it a basic function now. Once you put the basic expression into an equation, if it's a function, then you can call it a basic function, or if it's in a relation, you can call it a basic relation. So if I did this, now it's like a basic relation. It's the bare bones x's, and it's also the bare bones y. You can look at the y as well. So it's not like it's this. With a function, you don't have to consider any changes when it comes to the y because you're pretty much just taking the y and replacing it with f of x. It's all done, the shifting is all really done on the x. But with a relation like this, you could kind of think about, you could do operations to both the x and the y directly. You can still perform, like with a function, with any of these functions, you can still stretch and translate and everything about the y-axis. It's just not quite as explicit here as it is here, for example. Like you're not directly, it's just a little bit, it just looks different. It just looks different with the function notation. And I'll try and explain this in the next video. But again, this is the basic expression. This is the basic function. Here's the graph of y is equal to x cubed plus square root of x. This is where you're starting. Starting with this basic expression or basic function, everything that we're going to learn in the next video, you could shift this about the x or y. You could stretch this or shrink it about the x or y, you could flip this about the x or y axis, starting from here. And that's what I meant by, you want to be able to recognize or look at any function or relation and see through it to what's the basic form of it. In this scenario, this would be the basic form. You would say the basic form is a cubic added to a square root. And so what you can see is there are a finite number of parent terms, and I'm going to go over the majority of the parent terms in a second. There's a finite number of those, but there's an infinite number of basic expressions because you can combine parent terms in an infinite number of ways. I could have divided x cubed and square root of x. Well, in that case, sometimes when you combine them, it actually simplifies to a parent term. So if I did x cubed divided by square root of x, that's x cubed divided by x to the 1/2, which is x to the 5/2. And so that's, this is a parent term, x to the m over n. I would categorize this as a parent term, x to a fractional exponent. But parent terms can be combined in other ways. Here we just looked at adding, subtracting, or multiplying or dividing, but a parent term could be contained within another parent term. So maybe we have y is equal to the absolute value of the cube root of x. This is a cube root contained within an absolute value. Or maybe, so we haven't learned about exponentials and logarithms yet, but I'm going to include them in this video. But maybe you have log of x cubed squared. So this is a cubic contained within a logarithm, and all of that's contained within an x squared, a quadratic. That's how you have to look at it. This is a cubic contained within a log. That's all of that is contained within a squared, and it hasn't. But this is the basic form because there's no coefficients. There's no shifting or anything. Nothing has been done with this as far as transforming it. Here's this log of x cubed squared. You might say, well, look, it's been shifted. Well, no, that's kind of that log of x is naturally, just as it is shifted off of the origin. Okay, but again, from here, based on what we're going to learn in the next video, you could shift this to the left or right, shift it up or down, stretch it about the y-axis or shrink it about the y-axis, same thing about the x-axis, or you could flip this about the x or y-axis, all starting from here. Okay, so what are the parent terms? What are all of the potential parent terms? And again, what is a parent term? It's just the most basic form of any type of algebraic operation that we have defined in math. Well, we can start with just x. So this is f of x is equal to x, or y is equal to x, but I'm just putting it, again, I'm putting it just as a term here to indicate that this doesn't have to be part of a function. You could make a relation. I could make y squared plus y minus x is equal to 3. Here's a relation. This is not a function, but I've used this parent term as part of this relation here, you see? But for each of these parent terms, I'm going to show the graph y is equal to that parent term. And just to point out before we get into this, note that if you take any term, algebraic term, and even expression as well, pretty much any algebraic expression, unless it's an out of the ordinary expression in the sense that like the quadratic equation has a plus or minus in it. If it's not something like that, then if you just set that expression equal to y, it's a function. Note that, okay? So like you might be saying, well, how is that the case? I mean, what if you have like an even root or something? Well, no, because if you have an expression, I could have the craziest expression I could possibly think of. So again, we're going to include I know we haven't talked about logarithms yet in the course, but I'm just including logarithms and exponentials in this video. Don't worry about if you don't really understand exactly what they mean. But if, I could have log of square root of x plus x to the 3/2 minus absolute value of x squared. I mean, I could have anything I want. When you think about if I just set it equal to y, that's a function. This is a function because y to the first, not like y squared or anything, just y to the first. Because even if you have an even root, remember that's a principal root. The plus or minus only comes into play if you add that yourself, if you add that radical yourself. Here, this x to the 3/2, that has one output. This is a principal root. You return the positive root. So the vast majority of the time, if you have some expression that's just a function of x, like an expression of only x or one variable, no matter how complicated it is, the vast majority of the time, if you just set that equal to y, that's a function. Unless that expression has a plus or minus in it, well, which is rare, like the quadratic equation or some other kind of weird function that specifies that it's returning more than one output. Okay, so the different algebraic terms that are defined, that we define in algebra, that we defined in pre-algebra, and also including what we haven't gotten to yet, logarithms and exponentials. What are all the different algebraic terms? Well, okay, just x. Y is equal to x to the first. A line. Graphically, this is the basic form of a line. Starting from here, you could move it left or right, stretch it vertically or horizontally, flip it. But the most basic form of a line is just x. So y is equal to x is how you would think about it graphically. Okay, what's next? Well, you could raise x to a power. And let's start by thinking about an integer other than 0. I talked about what you could think of 0 like a constant. X to the 0 is a constant, which is also a parent term. But outside of x to the 0, x to a negative integer, x to a positive integer, other than x to the first. We just talked about x to the first. Okay, now from here, I'm separating it into categories. This is all personal preference. You can do this however you want. This is my opinion on how I would look at parent terms, but there's nothing official about this. But I'm separating it into categories based on the resulting graphs. If the graphs are different looking, then I'm separating into different categories. If the graphs are similar looking, then I'm not separating it. So if this integer is greater than 1, then you could have the case where n is odd or n is even. So like x cubed, x to the 5th, x to the 7th, or x squared, x to the 4th, x to the 6th, etc. Here's what the graphs look like. So x to an odd number integer is a parent term, and x to an even number integer is a parent term. Now, if n is less than 0, these are in their own specific category. You have that negative integer could be odd or it could be even. That's where you see these asymptotes, where it's as x approaches the value that makes the denominator 0, the equation, the function is approaching infinity. 1 divided by x, if you get close enough to 0, you're just ballooning to a huge number. Okay, now just to make this clear, the idea is you could say, all right, you've got x to the 5th plus x to the 3rd plus x to the minus 2. Here is a basic expression that you can't simplify anymore, and you would say, okay, I'm combining a x to a positive odd integer with another x to a positive odd integer with an x to a negative even integer. But these are the same category, so you could say that you're combining an x to an odd integer exponent with an x to a negative even integer exponent. It just depends on however you want to do it. I'm saying that because here, if you're adding two of these, x to the 5th and x cubed are going to look similar. You're going to get something, again, that looks like this. X to the 5th plus x cubed is going to look something like this. It's look very similar. But you can do it however you want. I'm just trying to give you a sense of this. Okay, now you could have x to a fractional exponent, and you could break this down for when the fractional exponent is greater than 0 and when the fractional exponent is less than 0. And then you could break it down further. So if m over n is greater than 0, then m over n could be less than 1 or it could be greater than 1. So like, for example, x to the 3/4 is this, or x to the 7/5 is this. And then you could break it down further where for the m over n is less than 1, m is odd, n is even, m is odd, n is odd, m is even, n is odd. But you wouldn't have m is even, n is even, because that would simplify to something where an odd and an even. So you get these different looking graphs. This is like x to the 3/4. This is like x to the 3/5. This is like x to the 2/5. This is like x to the 7/4. This is like x to the 7/5. This is like x to the 8/5. Okay, same idea here. If m over n is less than 0, here you would have things like x to the, here would be minus 3/4. Here would be minus 3/5. Here would be minus 4/5. And then here would be x to the minus 7/4, x to the minus 7/5, x to the minus 8/5. But you don't have to break it down this way. I'm going into this level of detail for the sake of illustration. You can think about it however you want. I just did it this way because you can see all these graphs are different. All right, here's the absolute value of x. But notice this is a little different. The absolute value is a little different. It's more like an operator than it is than something like x squared is. You put a term inside of the absolute value. So when you think about the absolute value, they put absolute value of x. So they're putting the absolute value of x to the first. But you can do the absolute value of anything, x squared, x cubed. So I just put some examples of absolute values of different types of parent terms. With an absolute value, all you're doing is for any portion of the graph in the negative or positive x region, any portion of the graph that's less than 0, that's below the x-axis, that flips up. It's a mere flip to above the y-axis. So here, or to above the x-axis. So here, y is equal to x goes down, right? It's just a line, but the absolute value, this negative region, you flip it up. X squared is never negative, so nothing changes. X cubed does something like this. So look, it flips up. The negative region flips up. But even if you had this negative region in the positive x area, that would flip up as well. All right, here's exponentials. B to the x. B could be less than 1. B is greater than 1. This would be the parent term, the basic term. Here's log base b of x. Just as plain as it gets, right? As plain as it gets. There's not a 2 here. There's not a plus 3. You don't have log base b of x plus 2. As plain as it gets. Here's trigonometric functions, inverse trigonometric functions. Okay, and that's the only ones I pulled, the only parent terms I pulled. But there's more than that. You have like hyperbolic functions, like sine h of x. I mean, there's more out there. I think you get the idea. There are a finite number. If you could do research and get there are a finite number of defined like operations, mathematical operations on a variable. There's a finite number of those. But there's an infinite number of ways that you can combine those. Adding, subtracting, multiplying, dividing, or having one contained within another. And that's the distinction I'm making between a parent term and a basic expression. A basic expression is a combination of parent terms, but it's still basic. You can't simplify it anymore, so it's still basic. It still has no transformations applied to it whatsoever. And here's rational expressions, but I look at this as this is a combination of polynomial terms. So you have polynomials here, like here's a polynomial, but this is really what we're going to see in the next video is that even a polynomial like this, 3x squared minus 2x plus 9, this is the basic expression here is a squared. Because any polynomial, whatever the order of the polynomial is, that's the parent term, is the order of the polynomial. Because you could factor this, simplify it into a form where you can see all of the transformations that were applied to the parent term. I could turn this into like a 3x plus 2 squared minus 4. And then so I could see all of the shifts and stuff that this is. And so with a rational expression that's a ratio of polynomials, all that is it's a combination of x to the positive integer power terms they're dividing by each other. So I don't really include this as a parent term. This is just polynomials, but again, I could do log of x cubed divided by the square root of x. Here I'm combining, this is a basic This here is a basic expression. It's a basic cubic contained within a log, and that's divided by a basic square root. Now, you could have a case where you've got a basic term combined with another term that's not basic, it's like been transformed. So if I had x minus 3 log of x cubed, well, here I've got a basic cubic contained within a logarithm, and that's divided by a square root that's been shifted. That's been transformed. I'm not going to say what's been done. It's been transformed. Now, what does that exactly does that mean for the graph and all that? Because we have one portion of the expression transformed and not the other. Well, this is actually a term here. This whole thing is a term, but I'll talk about that in the next video. Okay, now just a reminder before we start with section 2.6, you can combine parent terms to make relations. And everything we're going to learn about transformations applies to relations as well. Here are some relations. So you've got a squared that's been transformed a bit, multiplying with another squared that's been transformed. I mean, you could actually look at this. If you combine all these, you would get a 2, 4, 6. You would get a x to the 6 that's going to have like some been transformed, x to the 6 plus, you'd have to look at it. Okay, but so these are all obviously relations. They don't pass the vertical line test, but you could transform this as well. You could shift this entire graph left or right. You could stretch it, flip it, using all the same operations that we're going to talk about in the next video. And I'll go over how those operations would apply to something like equations like this as well.